Swayam Prabha. Digital India. Educated India.
Welcome back to our lecture series on advanced hydraulics. In last class, we started the module 4 on hydraulic jumps, if you recall them. So, especially in the last class, we introduced to you the concepts on rapidly varied flow. What are the different types of rapidly varied flow? We also discussed on what is the difference between rapidly varied flow, uniform flow and gradually varied flow. For example, in uniform flow and gradually varied flow, you were able to take the parallel flow assumption, whereas in rapidly varied flow, it is not possible, and you have also seen that the streamlines have quite a good curvature. You were also introduced on hydraulic jumps. We also gone through in which all locations or in which all situations hydraulic jumps are formed. Today, as we discussed in the last class, we will go through the theoretical aspects on the hydraulic jumps, some of the theoretical aspects that are required, some of the fundamental principles, how you can employ them even for analyzing hydraulic jumps. This we will see them. So, just recalling back, hydraulic jumps mean it is a type of rapidly varying flow that occurs in open channels, or the definition it was given like that: when a supercritical flow meets a subcritical flow, this causes a jump in elevation of water surface and is called hydraulic jump. So, throughout our open channel hydraulics course, we have used the control volume or continuum approach. For analyzing the fluid flow in open channels. So, the same approach will be again maintained here for analyzing the hydraulic jump as well. What was the fundamental principle for any phenomenon? What was the fundamental principle you used in control volume approach? If you recall them, for any control volume, we have suggested that the Reynolds transport theorem can be used for analyzing any extensive property in a control volume. If we are taking the hydraulic jump as a control volume, the entire jump portion, if you are taking it as a part of the control volume, and if you are trying to analyze them, the same Reynolds transport theorem should hold good while analyzing the flow phenomenon in hydraulic jump. So, what was the Reynolds transport theorem? If you recall that, the material derivative of any extensive property B, this is equal to the rate of change of that extensive property stored inside the control volume plus the net outflux of this extensive property across the control surfaces of the control volume. So, if you have a cubical shape as a control volume, you know that it has now 6 surfaces, that is forming this control volume. 6 surfaces are there. So, what is the net outflux from these surfaces that is being given by this particular term? The change in the extensive property, the rate of change of extensive property stored inside this control volume, that is given as the first term in the Reynolds transport equation, if you recall them. So, we have seen that some of the extensive properties are mass, momentum, force, etc., and all. Similarly, again we are going to use the Reynolds transport theorem for analyzing hydraulic jump. So, just let me write it again, d by dB by dt is equal to dou by dou t of the first term is the rate of change of extensive property stored inside the control volume, plus the second term is the net outflux of this extensive property through the control surfaces. You know B is equal to the extensive property beta was called as the intensive property, right. Now, what happens if you are taking say conservation of mass? If you are taking the conservation of mass property, then the extensive property B becomes the mass of the liquid. Then you can see that say the hydraulic jump say in this hydraulic jump, if I am going to consider this if I am going to consider the control volume in the following form. Say this control volume is now enclosing the hydraulic jump. So, in our open channel flow predominantly we consider the flow as a one dimensional in the flow direction, right. So, therefore, this particular control volume is having only two surfaces which allows flow through it, that is on the left side and on the right side. So, that phenomenon we will be taking into care here. So, when in the Reynolds transport theorem, if you have taken the extensive property B as a mass, then I hope you remember the intensive property beta is 1, then subsequently the conservation of mass equation as per the Reynolds transport theorem was given as 0, means the net change, the rate of change of the extensive property, that will be 0. Mass can neither be created nor destroyed, right. So, based on that same principle, now you will be getting rho du plus control surface rho v dot n dA, right. So, this equation now we have to apply it for the following control volume. How we are going to? What is the first term? The first term dou by dou t of control volume rho du, as inside the control volume you have that control volume. Now, inside that control volume you may see that here inside this control volume you are not adding further water or you are not detecting amount of certain water within this control volume. So, therefore, the first term will be 0. So, it becomes a 0 quantity. Therefore, your control volume equation, Reynolds transport equation becomes for the conservation of mass becomes rho v dot n dA is equal to 0. That is the net outflux of mass through the control surfaces of the hydraulic jump, that will be 0. That is the meaning of this particular term, that is the net mass outflux through the control surfaces of the volume is equal to 0. That is the meaning of the entire equation now. So, as we mentioned earlier, there are only two control surfaces that allow flow through the control volume. So, which are they? So, we have in the pre-jump section or the upstream section, that is the pre jump section or the upstream section of the jump. So, again just for your benefit I am just drawing the hydraulic jump. It shows that. So, your control volume is like this. So, on the left hand side the section will be maybe in this form. So, the depth of flow, let me give this as y 1, the area of flow is A 1, right, and on the right hand side this control volume, this surface allows flow, and as you know the depth of flow increases in the downstream section. So, we are suggesting a higher elevation and it is being given as y 2, fine, and the area of cross section is given as A 2. So, what does this equation mean then? Therefore, your equation rho v dot n dA, this integration is equal to 0. It is nothing but you have now two sections, left hand side and right hand side. So, what is the net outflux to these two surfaces, that you have to combine now. So, as we know that we used to take the average velocities in the sections. So, this average velocity into area can be combined for this entire integral term. As in the left hand side the outward normal is opposite to the flow velocity direction. Therefore, this is a negative quantity. So, I can write this quantity now rho v 1 bar A 1 plus rho v 2 bar A 2 is equal to 0. That is v 1 bar A 1 is equal to v 2 bar A 2. This is equal to discharge Q. This assumption based on the incompressible flow assumption, the density of the liquid is not changing. Based on that assumption, we are able to write it in the following form. So, you are getting a constant discharge, that is the discharge on the upstream side of the jump as well as on the downstream side of the jump, both are same, both are having same discharge. Here also it is Q, here also it is Q. That is the meaning of this equation. So, from the conservation of mass equation, you are now getting the following relationship. So, what happened? I mean, applying the momentum principle. So, if you apply the momentum principle to the control volume, same control volume, if you apply the momentum principle, you know that the extensive property B is now equal to mass into velocity, right. Therefore, the intensive property is taken as V. Again, the Reynolds transport theorem, the material derivative of B, that is m V, this is nothing but equal to dou by dou T of volumetric integral V rho du plus the surface integral that gives you the net momentum flux that passes through the control surfaces of the control volume. So, this is the first term shows the rate of change of momentum stored inside the control volume, right, and this term shows the net outflux of momentum across the control surfaces of the volume. So, again let me suggest you are not adding any momentum inside the control volume, or you are not detecting any momentum from the control volume. Inside the control volume you are neither adding it or detecting. So, we can avoid the first term, that is we can suggest the first term as 0, dou by dou t of because we are not adding or deducting momentum inside the control volume. Okay. So, inside the control volume we are not neither adding or detecting it. So, that first term will be 0. So, this means that your momentum equation now becomes d by dt of m v is equal to the net outflux of momentum through the control surfaces of the control volume. Fine. What is this quantity? The material derivative of momentum, that means the rate of change of momentum in the control volume, that will give you the net force acting in the control volume. This gives you the net force sigma f, and the second term. So, I can write this entire quantity as sigma f is now equal to v rho v dot n dA, right. So, you have now two surfaces, right. Again only two surfaces allow the momentum flux to pass through it. So, you have the upstream section where the flow depth of water is like this. You have the downstream section where the depth of flow may be considered at a higher elevation compared to the first one, and you have the jump occurring in the channel. So, there is a jump. Okay, it may not be a realistic figure which we have drawn here. So, I can just draw it very close, this entire section now upstream. So, the jump between that short reach, it can be given here. Here the area is A2, here the area is A1, V1 is the velocity here, V2 means we are averaging it. I hope you remember that, V1 bar, V2 bar. The discharge is same in both the sections. So, the net momentum outflux through the control surfaces, this can be given as, here the outward normal vector is in this direction of that surface, whereas here it is in this direction of the flow itself. Therefore, the left hand quantity will be a negative quantity. So, I can write this now as rho into V 1 bar squared A 1 plus